We have another example problem here. A uniform meter stick is pivoted at its end and hangs vertically. If it is displaced from equilibrium by a small amount and then released, what is the period of the resulting oscillations? So meter stick is pivoted at its end. So the pivot is at the end. We pull it to the side a little bit and release. So it's going to swing back and forth like this. This is a pendulum, but it is not a simple pendulum because the mass is not concentrated at the very end. This is a physical pendulum because there is mass everywhere along the length of the meter stick. For a physical pendulum, we know that omega is the square root of mgl over I. Well, omega is 2 pi f, or 2 pi over t, so the period of a physical pendulum will be 2 pi times the square root of I over mgl. Okay. So I is the moment of inertia, or also called rotational inertia. I will provide the table or the equation. I've copied the table in here. Now, a meter stick is most closely a thin rod. So we need to decide which of these thin rod equations we want to use. We know this meter stick is going to rotate around its end, so we want to use the 1/3 ml squared for I. Now notice in the picture, L is the total length of this thin rod. So I'm going to come back up here. I know I is 1/3 ml squared. Now, in the table, they use a capital M. I've written it as a lowercase m. Either way, m is the total mass of the meter stick. So that is something that we're going to put in here for I. The L in here, this L is not the total length. This is the distance from the pivot to the center of mass. So a uniform meter stick means the center of mass would be in its geometric center. So at the 50 centimeter mark. This L in the equation, this lowercase l, is half of the total length of the meter stick. So I'm going to put that in here as well. Notice m cancels. One of these l's is going to cancel. So let's see, we're left so far with, we have an L, the 2 down here will come to the top. I'm going to go ahead and write the 3 in the denominator because that's where it is. So my 3 is accounted for, my L is accounted for, my 2 and G are accounted for. So this is the period of my uniform meter stick. So now I can plug in my numbers. The length, 1 meter, since we're dealing with a meter stick. G, 9.8 meters per second squared. So, calculating this. I'm getting 1.639 units. Meters are going to cancel. That second squared comes up to the numerator. I take the square root. This will be in seconds. So meter stick, I assume we have at most 2 sig figs. We know it's a meter plus or minus. So what did, yeah. So 1.6 seconds is the period of this meter stick. And this, of course, assumes no friction up at the top pivot point. So everything we've done so far is for ideal situations.